But thanks everybody for joining again. I'll stop here at about 10 or 15 after. So we'll talk today about radar, and what I'll do briefly is just kind of show you the way things are now, and we'll transition into what we see as the new trends in radar and how they can actually help your reliability and your uptime. I gave a brief introduction myself. I'm based outside the St. Louis area. If there's anything you take away from this presentation, I ask that you take away that our new 80 gigahertz radar is very simple and easy to use. I'm the offer manager, and I've been able to set them up in 2 minutes. I put a video on the internet of me doing that. It's on YouTube if you want to check it out. And if you take away anything from our 24 gigahertz radar offering, please remember the drop antenna. That's what you see here in the corner. Kind of looks like an egg. There's some benefits to that in that it works very well with condensation and buildup and things like that. The round-ish design certainly helps with that. So we ask ourselves when we started to look at releasing these new products, the new radars, what are our customers after? Why do you need radar? And first and foremost, we know you want to keep yourself off of the news. I don't need to go into any of these accidents to remind any of us that big oil and gas, hydrocarbon accidents, and they were all caused by either misapplied or unmaintained level instruments. And certainly we want to help keep you off the news by giving you what we see as a very valuable, easy to use level instrument to help you take stock of your tanks. And of course, just like anybody else, we go to Google to see what people are looking for. And when you start typing in things in Google, radar level transmitter 4, a couple of the more popular things that come back are water, which is, that's a pretty easy application, but powder and solids, which are very challenging. It's something we'll talk about in a minute. So we identified the powders and solids, as one of the potential problem areas that our customers out there in the field are having. By the way, if you see these little yellow boxes, if you want to learn more, please feel free. You can take a snapshot of the screener. Like Dania said, they'll give you the presentation. They're movies based on our website. They're designed to be brief. Some of them are real brief, 2-minute explanations of how some of these things work. Nothing wrong with any of the level technologies we're using now. What we see is very popular in the field are ultrasonics, density-based level instruments, and the lower frequency radar. But as you start to dig into these things, as you start to look at ISA chat boards, as you start to talk to customers, we find out that ultrasonics, while they work in many applications, they're not as reliable and robust as radar. They can't take the same pressures and temperatures and things like that. We use Schneider Electric. We have density-based level instruments, such as differential pressure level with our IDP-10S, or our buoyancy instrument, the 244LD. But again, those rely on having a specific gravity or density put into the instrument to get your accurate level reading. And it's something, if the density fluctuates, sometimes there's ways to compensate, sometimes not. And then the lower frequency radar. Early in my career, I go back to the mid-2000s when I started, we didn't have the same types of radars we had today, which kind of led to the presentation of new products. Sometimes there were issues with the lower frequency radar in terms of difficulty in getting them set up, in trying to get them applied properly so they didn't have false echoes and things like that. So we think we're on the right track toward getting that solved, which I'll explain in just a bit. One of the things we've seen the advent of, though, and one of the things that's been very popular for us has been guided wave radar. And why is that? Guided wave is very reliable radar technology because, as we all know, the radar signal stays confined to a rope or a probe. And by doing that, it works well with foam. It doesn't echo around. It doesn't get lost. And it doesn't bounce around like, maybe I say bounce, that's a bad word, but you get the idea, hopefully, that the radar signal can echo, create some false echoes and things sometimes with the lower frequency or misapplied free space radar. So what we think we've done, and we're leaning toward, if we can solve that radar problem, put something in a high nozzle, put something that can see through a ball valve or an isolation valve you may have on the top of the tank, and something that can actually work around the obstacles. And we think what we found, and we'll show you in just a minute, is the higher frequency radar has the capability to see around tank impellers, to see around heating coils, to see around obstructions inside the tank, and actually be installed in high nozzles and not have to worry about it. So I realize this looks like an eye chart, and I'll just take a minute to show this to you. We've worked with our salespeople So they can demonstrate this for you. And this is what's so important when it comes to, you can download this actually from, you can download this same chart, and it comes out as an interactive, we say interactive, it's an Excel spreadsheet for sure. But if you look at this chart, this displays our different types of radar. And I'll draw your attention, please, to the frequency you see here. 10 gigahertz, 24 gigahertz, and 80 gigahertz radar. I have to tell you, there is no one-size-fits-all radar. All these radars have a place in different types of applications, which is what, quite frankly, why we have the selection here. But if you say, I have a tank that is, say, for example, 3 meters tall, what this Excel sheet does for you, it tells how big that beam is going to be, and the recommended vessel width in meters. Now I'm used to working, I'm gonna, forgive me for a second, but I'm gonna go to feet, and we'll put in a 10-foot tank. So it tells me that a 10-foot tank, an 80 gigahertz radar with a 2 3/4 inch lens antenna is gonna be 7/10 of a foot wide, so roughly 9 inches. And the recommended vessel width in feet is at least 1 foot. On the flip side, if you go back to the traditional 10 gigahertz technology, which we've had out on the market for a few years, and you take an equivalent 3-inch antenna, that same beam is going to be almost 6 feet wide, and it's going to require a vessel that's almost 9 feet wide. And where this really comes into play, if you click on the next tab, and again, our salespeople can help you with this. So let's put in that 10-foot tank again. Our 80 gigahertz lens antenna, which is some of the new technologies we'll tell you about here in just a few minutes. A beam angle of 4 degrees. It says the minimum width of the vessel has to be 1 foot. So if you think of how big that beam is going to be, what we try to do is we estimate, literally look down into the tank, or hopefully we can get a drawing and understand, what the base internals of the tank are, and see where that beam's going to go. What is it going to intersect? One of our goals is to try to avoid obstructions in the tank, to avoid potential obstacles, and hopefully give you an increased reliability with your radar. So back to this, we call this our beam angle formula. And again, you can download it here and test it out, or work with our salespeople or somebody here at Schneider, and we can show you how to do it. So just to give you an example of what I'm talking about when it comes to beam angle, you may say, well, why is beam angle important? Who cares? Each different frequency, first of all, a general rule of thumb, the higher the frequency of the radar, the smaller the beam angle, which kind of defies logic. And also, the bigger the antenna, the smaller the beam angle. It goes into some of the mechanics and the physics of radar, but if you just remember those two things, generally the bigger the antenna, the bigger the antenna, the smaller the beam, the higher frequency, the smaller the beam. So let's take a traditional 10 gigahertz with a 3-inch horn antenna. It's going to put out a 32-degree beam angle. And I actually plotted this out in PowerPoint, which wasn't the easiest thing to do. So this is 32 degrees. And you can see my poorly drawn thermal wells in the side of the tank here. So the radar sends out its signal, and it says, hey, there's an echo here off of this thermal well. And oh, look at this one. Here's another echo. And here's the actual level. So we've got 3 echoes. We have to go back in as human beings and physically tell the radar. Sometimes the software will pick it up. Sometimes we have to do a little manipulation with things we call like an empty tank spectrum or a snapshot. Different manufacturers call it different things. But essentially, you can blank out these thermal well signals. You can tell the radar, hey, ignore this and just concentrate on this. And the radar goes, got it, cool, we're rocking and rolling. So let's look at another size of beam angle. This would be one of our 24 gigahertz radar, like the LR54 with a 3-inch drop antenna and a 9-degree beam angle. And here you see the 9-degree beam angle misses the first thermal well. It hits the second one. So we've got a little bit, we've got fewer problems. It says, hey, I see this thing here. It could be the level. It could be a thermal well. Some radars are smart enough to interpret that, the tank obstructions. Some we physically have to go back in and say, you know what, ignore that. The radar says, okay, got it. Now, we get to the new technology, 80 gigahertz. We avoid both obstructions completely. All this energy goes into our liquid. So we get a nice tight beam focusing its microwaves here, and we get a much better, higher reflection back. Versus if we go here, we're going to lose some of the energy that's going to echo off of this thermal well. We're going to lose some of the energy that gets echoes off of this thermal well. Same thing here. Whereas this now, rather than have something like an umbrella, we have a laser. It's not a laser, it's a radar, but hopefully that explains what you're looking at. So it's a nice focused 4-degree beam, a lot of energy down in one place, and you get that same energy back. So when we talk about the wavelength, I get a lot of questions about this, and I'll try and be brief. I don't want to get too into the weeds, but 80 gigahertz wavelength is a little under 4 millimeters. 24 is about 12.5, and 10 is about 30. Why is the wavelength important? Generally, the smallest particles, and I'm talking about solids and things that are measured, are 1/4 the size or half the size of the wavelength. So assuming it's 1/4, we'll get into the solid stuff in a minute, the 80 gigahertz can see particles as small as 1 millimeter. Okay, so I'll transition into solids in just a minute here, but I want to take just a second to address. I'll try and see if there's any Q&A. I don't see any questions, but is there anybody, Danny, are they able to open the mics, or is there anything I have to do if there's a question?
Hey, Jeff. Oh, go ahead.
I did see that Varun had his hand up. I don't know if that was a mistake or not.
Yeah, I actually just sent him a chat to see if he had a question, but he hasn't responded yet. So once they do, so they said, can you please explain the beam angle relation?
Beam angle relation. Could you elaborate a little more? Oh, so you're asking about the high frequency, basically why a high frequency radar may have a smaller beam angle, or a bigger antenna may have a smaller beam angle. I'm assuming that's it.
Yeah, exactly.
Okay. I'm gonna have to punt on that one. It gets into what I can do, Dania. Why don't I do this? Why don't I do a follow-up where I present a couple of slides and show some of the math that goes behind it, how we calculate like that. And maybe Varun, would that work for you if I posted that on the website, because it gets a little bit into the math and things like that?
No issues. Yep, that's
perfect. Thank you. Okay, good question. Thank you, Varun. So, all right, I'm going to go ahead and jump back into this, if that works. So when you take a look at this, would be a solids level application. We realized you have liquids, you have solids. You've got so if we go to the solids here, one of the things you have to look at, that same 80 gigahertz beam angle, it's going to look right below where you mount it to pick up the level. You can actually tilt it if you need to get an angle to get down into the cone. And the same thing with the 24. Remember, we've got a little bit wider beam angle with the 24. So you, rather than see a very small area of your solids level, you might get a little bit bigger average than you would with the 80 gigahertz. And where does this come into play? So I'm not going to say liquids are easy applications, because we're dealing with foam, we're dealing with turbulence. But if you think about solids, you've got rat holes, you've got bridging, you may have stuff that just clumps to the side of the tank, and you're not able to, you're not going to see movement along the tank walls or things like that. Consider this, if you will. The red dot simulates the 80 gigahertz, where that's going to see the solids. The yellow, excuse me just a second. The yellow, the 24 gigahertz, that's where it's going to see the level. So if we just put the radar on top of the tank and shoot it straight down, it's going to see the level here, 80 gigahertz, 24 gigahertz. And if we angle it, which is something I'll show you in a minute, you're going to hit closer to that angle of repose. So it's really up to customers, it's up to you to work with your salesperson or your engineer to figure out if seeing the level here is fine, and that's a good indication of solids level, that's great. But if you say, hey, I need to hit closer to the angle of repose, or I think I want to angle this radar so it can get down into the cone, that's something else you'll have to look at. And we do have a solution for that. So there's two things we have: an orientation kit, which allows you to tilt the radar up to 30 degrees. And then we have simple 2-degree flanges that you mount. So if you just need a nudge to move it off the wall, or you want to get it closer to that angle of repose, you can do that as well. But these are accessories that sometimes are common with solids radar. But consider this: you don't have to tilt the radar to see the angle of repose. If where it's looking at directly below works for you, then it's fine. It's not an issue. But if you want it to be able to see something different, you're going to have to actually angle it and make sure it gets a good representation. And this is one of the areas where I see potentially the 24 gigahertz radar, I think, may have some advantages here in the solids level application, because in solids level, what the radar and its algorithms are trying to do is actually smooth that into it. It's trying to see it as a nice level flat surface. It's taking what it sees and trying to average it out to give you a level. And you're going to get a better average or a better representation of what's going on if you use 24 gigahertz. The drawback is, remember, that 80 gigahertz, it's focusing its energy in one place. Solids level is often very, very, very low dielectric constants, things like polypropylene pellets, styrofoam, and things, very low dielectric constants. So many times in these applications, you're going to want to try to use that 80 gigahertz to give you the best chance at getting a nice, good reflective signal back, because again, it's very low dielectric constant. So we talked about the 80 gigahertz, and I ask you again to take this away. They're easy to use, very simple. Set up, somebody like me could set one up in 2 minutes, and it's going to focus that energy and allow you to put radar in places where you may not have been able to use it before. We didn't address the drop antenna very much, but it is something that is, I think, unique, and it's particularly helpful in solids level applications or places where you can get buildup. We have horns and we have drop antennas for the 24 gigahertz, but a lot of times this is going to be one of the choices I think you'll find. And if you look at this and you say, hey, going back to Varun's question about beam angle relation, I really like that nice tight beam angle. I like the idea of getting that energy focused. You can actually get a small beam angle with a lower frequency radar. It's just you have to increase the antenna size. So say, for example, you could get a 5-degree beam angle with a 6-inch drop, or with a 6-inch drop antenna, or an 8-inch horn. So you can essentially get the same type of beam angle from a 24 gigahertz that you would from an 80. I'm going to move a little quickly through this. This kind of gets into some of the specifics regarding the specific models of radar. Just to give you a brief introduction, the LR54 is what I call our workhorse. It's a standard liquid level 24 gigahertz radar that works in many applications. The LR74 is like a big brother or big sister, if you will, to that LR54. You'll notice it's got a little bit of standoff here between the antenna and the electronics. It can handle a little bit higher pressures and temperatures. And it's got additional algorithms built into it to deal with heavy agitation and things like that. It does have a Metaglass dual seal as well. This is an 80 gigahertz. This is one of the things we've talked about today. The LR75 is our 80 gigahertz liquid radar. You'll note the antennas. In the pictures here, we put drop antennas on these. You can get horns, but with the 80 gigahertz, it's just what's called a lens antenna. It's smooth on the bottom. There's nothing that protrudes into the tank. So with this model in particular, if you remember back in the day when we used to put in radars, the application places weren't always ideal. Oh yeah, I put the radar in over there, 4 inches away from the tank wall. Well, a lot of times this is what an 80 gigahertz allows you to do. We can put radar in places where we haven't been able to put it in before. Many times we can see around obstacles, and we can get that nice strong reflection back to increase our reliability and get a good signal. So to solids level radar, we have a 24 gigahertz, the LR64 for solids. and then the 80 gigahertz, the LR65. And if you're thinking to yourself, well, why can't I just use, what makes the solids level radar so special? Why can't I just, mix and match? I'll get a liquid level for everything or a solids level for everything. Would you see a signal back? Probably, yeah. I mean, it's going to reflect and see something. But what we do differently, there are different algorithms in each type of radar unit, the liquid versus the solids, particularly the solids being a very challenging applications. We tell it to take signals at a much lower dielectric constant. We put algorithms in it to deal with dust up very near the filter, up very near the antenna, sorry. And we have algorithms that tell it to average out what it sees. So if you go back to that angle of repose and things, there's going to be algorithms inside the solids level radar that help deal with all the challenges that solids level applications have. So I hope this is interesting for you. If you're interested, obviously work with Cymark as your local rep. You or they have access to our Buy Automation website where you can log in and work with them to specify one, or fill out one of our questionnaires to help get you going. And there's some suggestions in the questionnaires that help us get very specific at times. But if it's something you can work with to just fill out as much as you can, it generally helps us get started on a level solution for your application. So the LR75 comes in, just a standard one, just over 4,000 Canadian dollars list price. The LR65, which is the 80 gigahertz for solid, just under $4,000. And these models are just suggestions. I put them up here just to give you an idea of what something costs, a suggested model number, but it's just that, it's a suggestion. And we all know when we're dealing with hazardous areas, hazardous chemicals, hazardous substances, we have to be precise when we deal with the instrumentation. So please either consult an expert or your local representative to help you, Cymark, to help you find exactly what you're looking for. If you're interested in more, we have a collaboration website. It's called Schneider Electric Exchange. It's in no way a substitute for our technical support group who answers those questions, and as well as your rep. But it is a place to bounce ideas. What type of weather protection should I use? Have you ever done a polypropylene pellet application? What would you recommend for this? It's exactly meant for that. So with that being said, I'm going to stop right here and turn it over for questions. Can you hear me, Dania?
Yeah, absolutely.
Okay.
And if anyone has any questions, feel free to just raise your hand and then we can chat it with you, or you can put it in the Q&A little box down in the bottom.
Cool.
As well as if you don't want to ask your questions and you got any questions, you can email me or Curtis or your Cymark representation, and we'll get them answered for you.
Absolutely.
Cool. So, and what I'll do just as a follow-up, I'll do a couple slides or a little movie about the beam angle relation for you to put on your website or your blog, Dania, and that'll answer Varun's question, and hopefully maybe it's something some other people would like to know about.
Absolutely. And just as a reminder, we will post a video to the presentation on our YouTube page, and we'll shoot it out to all of the attendees, and then we'll also include Jeff's slides as well.
Cool.
Looks like we do have one question here from Varun again. How can we do cost reduction in manufacturing without disturbing the performance parameters of radars?
I guess when you talk about cost reduction, so if we talk about the installed cost of a like a DP level or something like that, the way we look at it, it's about I put some prices up there, $3,000, $4,000, hopefully to give you a peace of mind. And I'll give you an example when we talk about redundancy. You think about what's the percentage of cost of level instrumentation in an overall project? Maybe 10%. So for a few thousand extra dollars, you can have the peace of mind that you've got an accurate, reliable level instrument that can help you track and give you peace of mind that if your primary fails, like you go back to any of the accidents we talked about, Buncefield, Texas City, Capico, Puerto Rico, they had their primary instrument fail, and they didn't have an adequate backup. And for $3,000 or $4,000, preventing that $1 million spill that gets into the fuel system, the electrical system, and the water system, hopefully can save you some peace of mind.
Perfect. Any other questions at all?
I'll volunteer one more thing. If you're looking at, we try and think outside the box, and this what you see on the slide, the 24 to 77. Most new cars now are going to 80 gigahertz. I say 80 gigahertz, it's the same, relative area. They're going to the high frequency radar for the same reasons we talked about, that increased reliability. That you're going to get higher resolution and better accuracy. And if you want to check that out, I encourage you to take a look and learn a little bit more even about what's happening outside of our industry. The tighter beams and the increased reliability are helping drive our cars in many cases, and sometimes autonomous vehicles. So that's it for me. I really appreciate it, Dania, Curtis, Justin. Anything else from you guys?
No, that's it. Thanks, Jeff. We really appreciate it. I know as we launch these products, this is a global launch of new products from us. So I know you're busy launching this all over the globe. So I appreciate your time to present to us here in Canada, and to everybody who joined. Should you have any questions, again, reach out to Cymark, reach out to us. We're here to help. And thanks again for everybody's time.
There's one more question there.
Yeah, we have one just